So my name is Rasmus Lou-Møller. I'm the Director of Engineering for Ferroperm Piezoceramics, which is a part of CTS. And I'll be holding this webinar today about application-specific shaping technologies for piezoelectric materials. This is number 5 webinar in the series of 6 webinars, and the last one will be next week. Same time, same channel, and it will be on lead-free piezoelectric materials. So I'll be having that as well, and I hope you will join for that. So hopefully everything works now, and we can move on to application-specific shaping technologies. So this will be about technologies that are still used to make devices and are, you could say, adjacent to ceramic technologies. So here we'll be focusing on films on substrates mainly, in contrast to what we're used to, namely bulk piezoceramics, which comes in the shape of discrete components that have fairly simple shapes and are electroded and then are assembled into a device. So the alternatives that we're going through here will be novel technologies to enable miniaturized and novel devices. So I'll be touching on 2 topics. The first one is piezoelectric thick films, which is still a ceramic technology, and then I'll go into what we call PiezoPaint, which is a technology that we developed over the last years, and this is not really a ceramic anymore, but it's based on some of the same materials that we have in our portfolio. So that's the plan for today. Piezoelectric thick film. So the drivers behind developing piezoelectric thick film is basically to open up the application space possible where you would like some kind of a piezoelectric actuation or sensing. So some of the applications that we have in focus here is high-resolution imaging devices, and that require high frequencies. And by high frequencies, we're talking about 10 megahertz and above. Here it says 15 to 20, but we are normally operating in the range of 10 to 50 megahertz for these kinds of devices. And for bulk ceramic or conventional bulk ceramic technology, this can be a challenge to machine parts that enable those frequencies. Then we have another application space, which is miniaturized ultrasonic devices or actuators. And this is just trying to approach the problem of making things smaller in general in electronics and integrate the piezoceramic into MEMS or other miniaturized devices. And then, of course, there's a big driver, which is cost reduction. So if we're able to make things smaller, if we're able to be smart about the manufacturing processes, we can make things cheaper. So some of the key features we're looking for is for thick film is being able to manufacture miniaturized devices and having fairly low prototyping costs, still enabling high volume production, having high lateral resolution, meaning that we want things to still be at a high quality, even though it's miniaturized. So we need high resolution on the features that we can make, and then of course high frequency and high sensitivity of the material. Then we also want to make a thick film that can be deposited on various different substrates. And The image that you see on the picture here is just one example of a device, which is a demonstrator. It's an accelerometer that is made using MEMS technology and thick film. Okay, so what is it exactly that we're talking about in the case of thick film? Basically, you have to imagine a ceramic film deposited on a substrate. And the way to do that is to take the powder, this piezoceramic powder, and mill it into a reasonable particle size, and then disperse that into an organic vehicle. So you get a paste, and the paste can then be printed using conventional screen printing, which is demonstrated here in the little animation. And then you can basically utilize the advantages of screen printing technology to make a thick film, a ceramic thick film on a substrate. And that includes scalability, volume, low cost, and of course the resolution that screen printing enables. An alternative process that we developed at Ferroperm is pad printing, piezoelectric thick film. So pad printing is well known for printing graphics on curved substrates or surfaces like pens, golf balls, Christmas balls, and so on. And the way it works is that you have a steel cliché with a pattern etched into the surface, and then by scraping a doctor blade over the steel cliché and the paste, you can deposit the paste into the pattern in the cliché, and then the pattern or the paste in that pattern is transferred to whatever surface you have using a soft silicon pad. So this is kind of illustrated here in the drawing on the right. And then you're able to not only deposit on flat substrates, which is what screen printing is capable of, but also on curved and any kind of surface that you can imagine that you would want to print on. So these are some of the substrates that we've tested in the past, and of course I mentioned the silicon MEMS substrate, but we also have ceramic substrates. We try to print on LTCC, low temperature co-fired ceramics, and even on stainless steel. And of course, the requirement for the substrate is that it has to withstand the firing temperatures that the thick film is seeing. So that's temperatures up to 800, 900 degrees C, meaning that that's the kind of durability requirement for the substrate. Steel is right on the border, so some applications might not be well suited for steel, but anyway, this is where the limitations are and the opportunities. So I'll talk a little bit about one of the more successful applications that we have where we've been using thick film. This is high frequency imaging. So the device that you're seeing here is a device with a thick film pad printed on a curved surface of a porous ceramic substrate. And this is done by pad printing. So you can imagine a curved thick film with a certain thickness, and then by exciting the thickness mode of that thick film, we're able to emit an ultrasound pulse at a very high frequency corresponding to that thickness. So that's how we get up to the tens of megahertz range. And the properties of the thick film and the substrate are such that you get a very wide bandwidth transducer. You get a very damped pulse at very high frequency, which is really good for imaging. This lends itself to very high volume manufacturing of high frequency transducers, and this is one of the successes that we had in the past. So and present, where we're manufacturing hundreds of thousands of these transducers, and have been since 2012. And these transducers are used in medical application that I'll talk about here. So this is an application by Althera, where they're using the transducer for imaging skin. So this is an application that is an alternative to a facelift, basically. So they are in one transducer or application emitting ultrasound at the fairly low frequency but very high intensity into the skin to make small lesions or activate the layers underneath the skin to tighten the skin. And then they have integrated the high frequency imaging transducer that I just talked about into the applications to do imaging during this treatment. So that enables monitoring while treating, and this is a very interesting application that's been successful for a while now. And so this was about a single element transducer using thick film, and of course the next application you would have in mind is, why not make arrays? So this is something that we worked on as well. If we think about the conventional way that arrays are made for high and low frequency, is that you have some kind of assembly process with the discrete components. There's a backing layer, there is a PZT element, and then electrodes, obviously, and then a matching layer. So this has to be individually manufactured and then assembled somehow through a bonding process. Then you can dice it up to make your composite usually, or to make discrete array elements. And then usually there's a dice and fill processing step as well. So this works quite well. It has some limitations in terms of assembly and costs. So the alternative that we're proposing is to do everything by printing and using thick film technology. So instead of having an assembly process, you basically print the various layers on the substrate or the backing layer, similar to the single element high frequency transducer. And the benefit of that is that you can, in principle, you can print on any kind of curved substrate using pad printing. You can also print on a flat substrate, and you can pattern the different layers just by the design that you want. So a lot less machining processes involved. And this is something that we have done in the context of a project. And I just have to apologize for the Megit logo here. It's from an old project when we were still part of Megit. But this is the concept basically. So printing the array directly on a substrate without any assembly or machining, and enabling the different array elements just by the patterning of the electrodes. And in this application, we were aiming at 10 megahertz. And this is what it looks like in real life. So you see here on the left side the actual transducer with the different array elements patterned by the electrode, and then you see the assembly with the PCB on the right and the connections. And This was done in a Innovation Found project together with BK, which is a Danish imaging company, and we're able to use their system to make some images with the transducer developed within this project, and these are some of the results here. So this was a proof of concept to see if the technology can generate an array that is able to do imaging, and further optimization has been done since, but the proof of concept is definitely there. Okay, so that was thick film, and then I'll spend the next 10-15 minutes talking about the PiezoPaint. So coming back to the drivers for developing this kind of technology, the ceramic technology, of course, has the limitations that you need to fire the ceramic at very high temperatures, up to, for thick film it's 800 to 900 degrees C. For bulk it's even higher, but of course that limits the application space in terms of what kind of substrates can be used if you want to deposit a film on something, and it has to go through this processing step of high temperature firing. So trying to integrate a film into polymers or textiles or even PCBs, that's going to be a challenge if you want to make a ceramic that needs firing. And we did see a call in the market for this kind of application space where we wanted to incorporate piezoelectric materials into textile or other garments in order to make wearable sensors and actuators. Also, we identified applications within medical ultrasound to integrate devices or print film on patches, or having wearable sensors where you had to have some kind of flexibility as well. So two things are necessary to accomplish that. One is, of course, the firing temperatures and the processing temperatures has to be low enough so the so the substrates can survive, and you need some flexibility in the material, which is not present in a ceramic. So here are some of the examples where you might imagine material like that would be feasible. So smart textiles, where electronics is integrated in the textile for sensors and actuators. Wearables, where you integrate sensors and actuators in clothing, either workwear or sportswear or whatever it is you have. So there are different ideas for applications there. You can have a buzzer in the collar, for instance, as a speaker or microphone. A motion sensor that detects the motion of the body, and so on. And then medical ultrasound, where you would have an interest in integrating an active element in the patches or various garments that are used in medical applications for ultrasound or for sensing or other applications. So that was the kind of the market drive, and then the solution that we're want to propose is, of course, piezoelectric. We cannot deposit the thick film that I spoke about recently, because it requires the firing temperatures, and so these are the challenges basically. We also want to make it printable and reliable, and we have to think about if it's textiles and garments and clothes, there's a washing requirement, so it has to be able to withstand some cycles of washing as well. And of course, low cost for high volume manufacturing. So this is the proposed technology. We call it PiezoPaint, and I'll just spend a few moments on the micrograph that you have on the right. So in the center there, across from left to right, you have an electrode deposited on a substrate, which is kind of the bottom part of the picture, and then the top part of the picture is PiezoPaint. And it's maybe difficult to see here, but all it is really is piezoceramic particles suspended in a polymer matrix. So it's a composite, and of course the piezoceramic particles, they enable the piezoelectricity, and the polymer enables the flexibility and the possibility to cure at low temperatures. So for the PiezoPaint, there's no sintering involved. It's just the polymer that needs to cure at a certain temperature. So that enables low processing temperatures. It has some cost in terms of sensitivity. So the sensitivity that we're achieving with this is a D33 of around 40 picocoulombs per Newton. And it depends a little bit on the processing. We have different approaches there, but this is the order of magnitude that we're seeing. It's still enough to enable some of the applications that we had in mind. Of course, it's flexible, and since it's a paste, it's just a powder suspended in a vehicle with polymer in it that can be dried. It's compatible with screen printing and pad printing, and in principle inkjet printing as well. And it has the same benefits as screen printing thick film in terms of scalability and cost for high volume. And this is what it looks like on a PT substrate. So we have printed a PiezoPaint patch on a PT substrate, and you see how it bends in this application. This is actually something we offer as a free sample for testing. So this can be printed on fabrics, textiles, composites, metals, obviously, plastic polymers, various types of laminates. Ceramics is also possible, paper even, and PCB, either flex PCB or regular PCB. And you can imagine other substrates that might be compatible, that can withstand the temperatures. These are just a very small selection of properties that we're able to achieve. So D33 in the range of 40, maybe 45 picocoulombs per Newton. We have a fairly high dielectric constant compared to other electroactive polymers. And in this case, it's compared to PVDF, which is the other flexible material, piezoelectric material that comes in mind when talking about these applications. So we think we have an edge with this material, and we've even tried to use it in certain demonstrators and applications. So you can see here on the top left, we've tried to do some NDT, non-destructive testing, on a composite structure, and by printing some piezo patches and emitting ultrasound into the structure, and see if we can detect the defects or holes in that structure. We've made sensors, motion sensors and buzzers on garments, and we're also looking into making some patches that are able to emit ultrasound into wound beds or into scars to have some kind of therapeutic effect on either scars or wounds. And this is one of the first earliest applications that we tested, which is just a simple buzzer. So just printing a piece of or a patch of PiezoPaint on a piece of garment. In this case, it's a lab coat, and we're able to measure an emitted sound by applying a voltage on this. So so that works well. I think let's see here. Yeah, so I think that brings me to the end of the presentation, and hopefully there'll be some questions that I'll be very happy to answer. So thank you very much. So let's see here, there's a chat. We can have a look at here. Yeah, so a lot of complaints about the sound. Thank you for that. Let's see here, is there going to be a question down here? It's working, all right. Very good. Okay, so there's a question about high voltage polarization after curing the PiezoPaint. Yeah, so that's a requirement. It's still a it's still a ceramic material that is suspended in an organic vehicle or in a polymer, so you need polarization. The domains will still be randomly oriented when you apply the PiezoPaint. So there's a polling step, and the polling voltage is higher, or the requirement for the polling voltage is higher than for ceramic, because you have the polymer basically screening the ceramic particles. So there's a bit of IP involved in that. Can the polarization be performed at the room temperature? Is it AC or DC? So it's a DC field, and the temperature that we're using is not disclosed. Usually we try to keep our polling conditions to ourselves, not disclosing that. Yes. Okay. Thank you. Very well. You are very welcome. So if there are no more questions, I say thank you very much. Hope to see you in a week, and we'll make sure that the sound works at the onset of that. So so you can hear me from the beginning. And thank you very much.